Hi there, my name is Miss Townsend and I love math. Welcome to Math with Townsend. This video is for grade 10 students who are working on the year-end summative. It's question number 15, which is from the trigonometry section. The question says, if the shadow of a building increases by 10 meters when the angle of elevation of the sun's rays decreases from 70 degrees to 60 degrees, what is the height of the building? So I'm representing the building with this structure here that kind of looks like a building. So, and I've made a nice sunny day here. So imagine the sun is in the sky somewhere and it is shining its rays down on us. So now if we picture the sun sort of here, there's my sun. I guess I could have made it yellow, but whatever. Directly overhead, in other words, we're not going to have any shadow because it's hitting directly to the building, and so even though the sun's rays are blocked at the top of the building, there's no ground on which to cast a shadow. But if we move the sun sort of lower in the sky, I mean, it's still pretty far away, very far away, but if we move it here, for example, now look at that sunbeam. It's going to actually, strike this corner of the building, and therefore there's going to be this shadow created by the building at that time. And the shadow is going to be here. So that's one of the sun rays triangles that I have to deal with. The shadow created here is because of the right angle triangle that we can see where the building is here, the ground is here, they're built at 90 degrees. And then we have this sunbeam, and all of the sunbeams that would be here are not here because the building is stopping them. And therefore we have this shadow zone which casts a shadow down here. So this would still be bright and cheery, and there'd be this shadow down here. So then later on in the day, the sun sets a little bit more. Oops. So we're going to set the sun a little bit more, so by 10 degrees in the sky. So there's the sun out in the distance. And now we have this situation where the sunbeams sort of stop because of the corner of the building, and now we have this shadow area. So all of this is in shadow, which means that there would be a shadow on the ground because there'd be no sunshine getting to this part of the ground. Sunshine over here, sunshine back here, but here no sunshine because the building is casting a shadow. So pretty clearly we have this situation where because the sun is 10 degrees more further down in the sky, the shadow has changed size. So I'll just show you both of them. So we have the original setting where the sun is at 70 degrees, and that creates this shadow. So let me just get a slightly thicker thing here. So that creates this shadow, and that is when the sun is at 70 degrees in the sky. So this angle would be 70 degrees. Then the sun sets a little bit, so it goes from here down to here, so it's setting in the sky, and now I have a shadow that looks like this. So like this. And that creates a different 90-degree triangle where we have a 60-degree angle, and we're told that the difference in the length of the shadow, so the shadow increases by 10, so that means that this distance down here is 10. So that's taking the information from the question and applying it to a diagram so I can figure out what to do next. So what I am going to do next is I'm going to separate this image into two separate pictures. So here we have one picture where the sun's slightly higher in the sky with a shorter shadow and a 70-degree angle for the sun. And then the sun sets a little bit, so it's lower in the sky, and that creates this longer shadow and a 60-degree triangle. So obviously I'm dealing with two right-angled triangles because that's how we like to build those buildings. And other than the 70-degree and 60-degree, what information do I know? Well, I know that this shadow being longer is X meters longer. Nope, I don't know that. I know that it's 10 meters longer. And I gave away my secret. So what I don't know is how long the original shadow is. So I'm going to call it X, which means that this shadow is actually X plus 10 meters in length. So that's something that I can tell you. Even though I don't know X, I know that if this shadow is X meters, then the longer shadow is X plus 10. So is there any other information that I know, or that at least I can compare between the two triangles? And there is. They both are shadows from the same building, and that building has a constant height. So in both triangles, this long edge here, the height of the building, I'm going to represent with h. And so that means for both triangles, I can talk about the tangent of that known angle being something with h and x in it. So here I can talk about the tangent of this angle being something with h and x in it, except for it would be x plus 10. So that's how we're going to set up the equation that will help us solve this question. So again, here's the information we just talked about in much less picture version, more pure math version. So I have the shorter triangle with the shorter shadow triangle. Here's the height of the building, and here's that unknown short shadow length. Short shadow, boy. Then later in the day, we have the same building, so the same value of h, but a longer shadow that is 10 units longer, and we're told that the angle is 60 instead of 70. And so if we set up our tangents, because for both triangles, if this is theta, then this side is the opposite, and then the close side is the adjacent, and that's the tan ratio. So for this first triangle, I can say that tan 70 equals opposite over adjacent, and for the second triangle, I can say that tan 60 is opposite over adjacent. So in both of these, now I have two equations, and in both of the equations, I have a height and I have an x. So I have two unknowns and two equations. So I'm now going to draw on my linear systems knowledge to solve for one of my variables. Well, for both eventually, probably. So if I multiply both sides, so here I'm going to multiply both sides of the equation by x. That gives me x times tan 70 equals h. Here I'm going to multiply both sides by x plus 10. So x plus 10 times tan 60 equals h. And that means that I have two equations, both of which are the value of h. So because the height of the building is the same, that means that whatever the height is equal to must be the same. So now I can say that x times tan 70 is equal to x plus 10 times tan 60. Now I have a single equation where there's only one unknown, and that's x. So if I take up my calculator and calculate the values of tan 70 is 2.7475 times x. Tan 60 is 1.321. So 1.321, is that right? I don't want to get it wrong. 1.7321. Yeah, that would have made a difference. 1.7321x plus 1.7321 times 10, which is 17.321. So collect like terms, I'll subtract 1.7321x from both sides. So those are both x terms. So let's collect them together. That's 1.0155x equals 17.321. And if I divide on both sides by 1.015455, I get x equals 17.1. So now I know the value of x. That must be the case in order to make all the information I have proper. So now if I just take either of my equations, let's take this one, it's simpler to work with, I can sub the value of x that I know and be able to calculate what the height is. So the original expression said that tan 70 equals height over x. So there it is. So if I just do 17.1 times tan 70, I will know the height of the building. And if I calculate that, I get almost exactly 70 meters. I think 46.9, 46.95, depends on how you round it. So I get a height of 70 meters. And if I had subbed that value of x into this equation instead, 10 plus 17.1, then I would have been able to calculate in this equation that h is also 70 meters, which is good. Again, it's the same building. So this was really just me checking my work. So I hope that was clear. Again, we had two right-angled triangles with two unknown values, but because they shared values, we were able to solve using linear systems. So again, the height of the building, 70 meters. I hope that was helpful. Go do some math. Please make sure you're seeking help as much as you need it to be successful in anything, not just math, but also in math. And thanks for watching.